So the hardware-based solutions to the critical section problem presented previously, and these solutions are complicated as well as generally inaccessible to application programmers. Instead, operating systems designers build software tools to solve the critical section problem. The simplest of this tool is the Mutex logs. So, Mutex log is uh, is the short for mutual exclusion logs. They are software tools designed to solve the critical section problem in operating systems. The purpose of Mutex logs is to protect critical regions and prevent race conditions by allowing only one process to access the critical section at a time. Here's how Mutex logs work. Okay, so when a process wants to enter the critical section, it first calls the acquire function. So inside acquire, a mutex log has a Boolean variable, often called available, and the acquire function contains a loop that continues to check the available variable. So available can be false or true, and if the log is available, it means that it's true. The process acquires the log by setting available to false, okay? And then it goes to critical section. If not, the process enters a busy waiting state, repeatedly checking until the log becomes available. When the process finishes its critical section, it calls the release function to release the log. So releasing the log sets the available variable back to true, indicating that the log is now available for other process to acquire. So mutual logs ensure mutual exclusion. However, one significant drawback of this approach is that it involves busy waiting. So when a process is unable to acquire the log because it's held by another process, the waiting process keeps checking the log in a loop, wasting CPU cycles. This continuous looping can be inefficient in multi-programming systems where CPU resources need to be utilized effectively. And semaphores, they are more sophisticated synchronization tool than mutex logs, and they offer additional features for coordinating the processes. Uh, and also, while mutex logs are straightforward and suitable for basic synchronization needs, semaphores are known as a more robust tool. So let's examine semaphores and explore their advantages over mutex logs. So a semaphore is a variable used to control access to a shared resource within the operating system. And mutex is simply a log acquired before entering the critical section and releasing it. And a semaphore is better for multiple instances of a resource, but a mutex is better for single shared resource. Here's how semaphores work. So a semaphore, denoted as S, is an integer variable that can be changed through two atomic operations. Semaphores operate through two atomic actions, okay? So wait, also called as down, as and signal, also known as up. Let's focus on their fundamental operations. So when a process wants to access a critical section, it performs the wait operation on the semaphore. And if the value is 0 or negative, the process is blocked until another process performs the signal operation. And if the semaphore value is greater than 0, it decrements the value. It decrements the value and proceeds. Yeah. So after a process exits the critical section, it performs the signal operation. Okay. On the semaphore, which is incrementing the S value. This operation can signal a waiting process and a waiting process. Yeah. Here's a practical example of how they can be used to solve synchronization challenges. Okay. Imagine we have two processes, process 1 and process 2. They are running concurrently, and we actually want to execute P2's statement S2 only after statement S1 in process 1. Okay, so to achieve this, we introduce a semaphore called sync. Yeah, this one. And it is initialized to 0. In process P1, after executing statement S1, okay, let me check. We use the signal operation to increment the semaphore value. And in process 2, we use the wait operation on the semaphore, ensuring that P2 will wait until the semaphore value is greater than 0 before executing the statement S2. So by setting up the synchronization mechanism, P2 will execute S2 only after P1 has reached the point where it signals the semaphore, indicating the completion of S1. So semaphores provide an effective way to coordinate the execution of different processes in a controlled manner.